Let's talk about the time complexity of this. So let's say that V is the set of all my vertices, therefore magnitude of V is the number of vertices. E is the set of edges, therefore magnitude of E is the number of edges. So in this example, the number of nodes is 1, 2, 3, 4, and the number of edges is 1, 2, 3, 4, 5. So the first step is set all nodes' distances to infinity and set the starting node's distance to 0. So this step is big O of the number of vertices, because for each node, each vertex, I have to set some value to either infinity or 0. Add 0, start to the priority queue, and let's assume that the priority queue is implemented using a min heap, because that would be the most efficient way to do it. Well, my priority queue is initially empty, so adding one element to an empty priority queue is just constant time, right? The priority queue is empty, I just set it as the root. So the next step is, while the priority queue is not empty, so this part's pretty tricky. Let's break it down step by step, and then let's try to come up with the overall time complexity of the whole thing. Popping the current element from the priority queue, theoretically, I could have every single edge in my priority queue. So this would be big O of log E. Because remember, if I have big O of E elements in my priority queue, or in general, if I have n elements in a priority queue, popping off one of them would be big O of log n, assuming the priority queue is implemented as a heap. Because the heap is perfectly balanced, I would just pop off one thing from a perfectly balanced heap. If the current node is not done, this is a constant time check. I would have some Boolean that I check. Mark it as done. This is constant time. I just mark the current node as done. For all outgoing edges from this node. So this is actually kind of tricky. Theoretically, my current node could have every single outgoing edge in my graph, right? So this is an example graph where if I was visiting this node here, every single edge comes out of this one node. So technically speaking, this would be big O of E edges. Checking this is big O of 1, right? Because this is just an addition, which is constant time, and then a comparison against the current distance, which is also just a constant time lookup. So this comparison is constant time. Setting a distance is constant time. Previous node is constant time. That's just setting a value. Adding something to the priority queue. Again, if I have n elements in a priority queue, adding one element to the priority queue is big O of log n. So technically speaking, without any other information, this single step could be big O of log E. I could theoretically have a priority queue that has all remaining, or all of the other E minus 1 edges. So adding this one would be big O of log E. So I've marked down the time complexities of each of the individual steps. Let's actually figure out what the overall time complexity is. As I'm doing my exploration, regardless of the structure of my graph, in the worst case, I have to add and remove every single one of my edges. This iteration is kind of coupled in with this while loop. Every edge is only added or removed once. I don't ever add any given edge multiple times. And I know that because the only time I add any edges is in this loop here, but I only enter this loop when cur is not done. So given that these are outgoing edges coming from cur, and I only do this for loop in which I add to the priority queue when cur is not done, and cur is not done only the first time that I see cur. So I'm only adding every single edge to my graph every single edge in my graph to my priority queue exactly once in the first case. I'm not adding any edges multiple times. So all of this overall is really just adding big O of E edges and then removing big O of E edges from a priority queue in the worst case. It could be that one node had all of the edges, or it could be that every node had exactly one edge. Either way, whatever the structure of my network is, every edge will get added exactly once, in the worst case. Therefore, the overall time complexity of this entire step 2 with everything encompassed in it is just the time complexity of adding big O of E edges to a priority queue and then removing big O of E edges from a priority queue, which is just big O of E times log E. So big O of V to add, to prepare, and then big O of E log E to actually do my traversal. So overall, this is big O of magnitude of V to initialize, plus magnitude of E log E to do the actual traversal.